This video was brought to you by Willem Deal, David O'Brien, and Grant Madigan-Kolstad. The video you're about to see showcases an exercise in pattern validation of land change simulation models that stemmed from an open invitation extended to the community of land change modelers to join in a cross-case comparison of land change modeling applications. Here is the relevant literature used to prepare this video. The legend seen here will be present across all cases, indicating blue as misses, red as hits, green as wrong hits, yellow as false alarms, and gray as correct rejections. Here are several of the cases submitted for the exercise, which included maps from Chodan, Vietnam to Santa Barbara, California. And here are the results from all cases, showing that the study of Pyrenees, Madagascar was the only one to have more hits than errors. During the course of map comparison, 9 challenges arose, evenly delegated between the categories of mapping, modeling, and learning. Level of detail is important when preparing data. High amounts of detail can result in complex patterns, and low amounts of detail can result in patterns that are easier to understand. For example, the data for the case of Pyrenees, Madagascar shows exactly one transition from forest to non-forest. In contrast, the case of Holland shows multiple transitions among 15 categories, resulting in a map that can be much more complicated to analyze. It is easy and problematic to select a number of categories that is so large that the analysis is intractable. Errors in the data may cause an illusion of land change. This can especially be a problem when there are a large number of detailed categories. It is remarkably difficult to create a time series of maps where the difference between the time points indicates true change on the ground. Some scientists should abandon the misguided belief that 85% map accuracy means that the map is acceptable, because 85% accuracy means 15% error. In most of our cases had less than 15% apparent change between the reference maps at the 2 time points. A second challenge arises in mapping when selecting a relevant spatial resolution. Spatial resolution is particularly important for 3 reasons. Spatial resolution can have a strong influence on results. Spatial resolution is something that modelers can usually influence, and it is not obvious how to select an appropriate spatial resolution. Spatial resolution is often determined by the availability of data itself, as was the case for the map of Marua, which used satellite imagery. The purpose of the modeling application and the scale of the land change process are also important factors when selecting a resolution. In the case of the map made for Worcester, Massachusetts, 30-meter resolution data was used. However, there are no stakeholders within Worcester who need an accurate prediction of land change to within 30 meters. 2 major types of land change are quantity difference and allocation difference, also known as net change and swap change. Net change is the difference in the size of the categories between reference times 1 and 2. For example, if forest grows more than forest loses during the time interval, then forest experienced a positive net change. All of the change in Pyrenees is net change because there is only one transition from forest to non-forest. Swap change exists when there is simultaneous gross loss and gross gain for a single category. Chodan is a case where there is 3 times more swap change than net change. This type of change is obvious in the maps of Costa Rica and Honduras. Swap change is especially challenging for multiple category transition models, especially when there is more than one category competing to gain from a single losing category. Now we will address some of the modeling challenges in the profession. Modelers must separate calibration data from validation through time in order to assess predictability through time. If modelers use data from both times 1 and 2 to calibrate a model of change between times 1 and 2, then modelers can measure goodness of fit of calibration, which is not the same as goodness of fit of validation through time. Examples of this are the cases of Marua, Kuala Lumpur, Haidan, Twin Cities, and Detroit, where the modeler used the correct quantities from time 2 to force the simulation to have 0 quantity error. Modelers should be explicit in reporting exactly which information from time 2 is used to calibrate a model of change between times 1 and 2. The figure of merit is a measure of overall simulation accuracy. This graph shows that lower simulation accuracies are associated with small amounts of reference change. Rare events are more difficult to predict accurately because the signals for both calibration and validation are weak. 7 of the 13 cases in this study showed less than 10% observed net change, and those cases tend to have lower accuracies than cases with more reference change. Quantity error occurs when the quantity of simulated change differs from the quantity of reference change. If the predicted change is greater than the reference change, then false alarms will be greater than misses. If the predicted change is less than the reference change, then false alarms will be fewer than misses. One must understand quantity error in order to interpret allocation error. The first learning challenge is to use appropriate map comparison measurements. Scientists have created algorithms to model landscape change, and there are many questions regarding which is the most appropriate map comparison measurement to use. Scientists should report the misses, hits, wrong hits, and false alarms because those measures give a clear picture of the validation and form the basis of many popular measurements for map comparison. It is helpful to use distinct measurements to indicate quantity error and allocation error. The relative sizes of misses and false alarms indicates pure quantity error. In many cases, scientists can use the total operating characteristic to measure pure allocation error. More information about the TOC is available at this link. The second learning challenge is to learn about land change processes. An important part of modeling land change is to increase understanding of the processes of land change. The Chodan example uses an agent-based model that is designed to gain insight into the processes of change. Agent-based models can require procedures to validate the process, rather than only the pattern. To maximize the learning of such processes, gathering information from validation exercises is key. It is also important for scientists to test the degree to which the past is useful to predict the future, because this allows scientists to measure the scales at which land use and cover change processes are stable over time. Methods such as intensity analysis can measure stationary according to the reference data, even without a simulation model. More information on intensity analysis is available at this link. Inaccurate predictions do not mean that the model is a failure, because validation can lead to learning regardless of the revealed level of accuracy. However, learning requires that the presentation of the methods and the results be clear. The third learning challenge is to collaborate openly. Scientists must create a culture where we feel free to share research and results honestly and openly, without a sense that we must claim that the model is somehow good, while lacking a clear definition of good. Scientists can feel professional pressure to make such vacuous claims of success, but such claims are not necessary for high-quality scholarship and tend to hinder progress in science. The criterion for acceptance of manuscripts should be rigor of method and clarity of presentation, not results concerning predictive accuracy, and certainly not empty claims of success. The legend shown here was used for cross-case comparison among the case studies in this exercise. Having the same legend across all cases allows for easy comparison of misses, hits, wrong hits, and false alarms, which ultimately results in scientists reporting unbiased results and sharing openly, honestly, and clearly. We thank these scientists at Wageningen University for contributing to this research. Please read Lessons and Challenges in Land Change Modeling derived from synthesis of cross-case comparisons. The manuscript goes more in depth concerning the lessons and challenges described in this video. You can obtain the manuscript at Professor Pontius's website listed here. Thank you.